didn't attend quiz 2, is there any problem in enter?
See, based on the, based on how we calculate the marks, actually, they need either, there are two formulas, right? So in one formula, they will calculate, they will choose the best among the quiz 1 and quiz 2. And another one, they'll take some part from quiz 1 and some part from quiz 2. So if you are, if you have good marks in quiz 1, and if, the constraint is so that you cannot attend, then I think it's no should not be an issue to if you won't attend quiz 2.
But overall weightage will get reduced and overall maximum possible 90%.
Right. So there will be some the little bit grade. I think. But if you are not able, if the situation is so that you cannot even go for a quiz 2, then
yes,
I think you have option. But try to attend it because it will be better if you attend quiz 2.
Ma'am, can you tell me any important tips for quiz 2?
Sorry, what?
Ma'am, I need any important tips for quiz 2.
Important tips, what can I say? You have to go through the content. Yeah, try to attend the revision session and try to solve as much problems as you can. So that means practice assignment and the previous year question papers. Those will help
Do you have PYQs for quiz 2?
PYQs means, yeah, there will be multiple choice, multiple select question in AT.
No, previous year question do you have, ma'am?
Previous year question. I think you guys already have previous year questions. In the link, I guess.
In AS grade, they have not shown the answers now.
Yeah, they haven't shown the answers. Okay. So, yeah, we try to give the answers there. And also TA will discuss some of the previous year questions. So that will be helpful for you. So if you join the TA session, so they will discuss some of the previous year question papers. Yeah, I'll try to upload the answers.
Okay.
Okay, so let's start. So today's topic is critical point and integration. So first we will understand what are the critical points and then how we can use derivatives to calculate the critical point of any functions. Okay, so before that, let's start with the maximum and minimum value of a function, or what we can say local maxima or local minima of any function. So what is local maxima and local minima? There are enough people. Start. So what is local maxima and local minimum? So if you have any function, so suppose the graph of function is given in this fashion, then if you consider this particular point, so point x is equals to a, then what is happening here? So in a neighborhood of this point, that means if you select one open neighborhood of this particular point x is equals to a, then the value of function at a, so that means the value f of a is actually greater than all the values function is attaining in this particular interval. So that means here what is happening? So that is the value f of a is actually greater than equal to f of x for all x belongs to this particular open interval, right? So let's name it to be some a minus h comma a plus h. That means for all x belongs to a minus h comma a plus h. So such kind of points are known to be local maximum. So local maxima means, function is attaining maximum value. And why it is local? Because we are considering very small neighborhood around the point x is equals to. We are not taking the whole domain. We are considering some part of a domain and saying that if at this part if at this part the value of function at a is the maximum, then we will say that this point is a point of local maximum. And similarly, we can define what do we understand by local minimum. So here again, so suppose you have any point x is equals to b, and around x is equals to b, if you are able to find a very small neighborhood means some open interval which contain b. So suppose this is your neighborhood b minus h comma b plus h. And what is happening? So the value f of b is actually the minimum value in this whole neighborhood. So that means here the value f of b is actually less than equal to f of x for all x belongs to the small interval which contains b. So that means for all x belongs to b minus h comma b plus h. So such points are known to be local minima. Again, why it is minima? Because the value of function is minimum. And why it is local? Because we are considering some part of domain, not the whole domain. So that's why they are known to be local maxima, local minima. So I'll give a formal definition. This is intuition. So definition is also same. So it's known to be point of local maxima or local minima. So the point x is equals to a is a point of local maxima if there is an h, if there is an h strictly greater than 0 in such a way that the value f of a is greater than equal to f of x for all x belongs to the small open interval a minus h comma a plus h. Then it's known to be local maximum. And similarly, we can define what is the point of local minimum. So the point x is equals to b is a point of local minima if there is an h strictly greater than 0 in such a way that the value of function at b is less than equal to f of x for all x belongs to b minus h comma b plus h. Right, the same thing. The definition is the same which we can define pictorially. Right, so this is a point of local maxima a, and this is a point of local minima. Now, what do we understand by turning point? So this local maxima and local minima are you can say that they are also turning points. So before turning point, let's understand what are the increasing and decreasing functions. Okay, so increasing function. So suppose we have a function f. Suppose f is a function from a set a to a set b, or let's take it to be real number. So suppose f is a function from real number to real number. Then we say this function f is increasing in particular domain. So that means this function f is increasing in the interval open interval a comma b if you choose any point between a and b in the increasing order. So that means this is your a, this is your b. So if you choose any point, so any 2 points, let's name them to be x1 and x2. So you are choosing any 2 points in between a and b, and in such a way that the value of x1 is actually less than the value of x2. Right? So that means x1 is strictly less than x2. Then if the function preserve this inequality, so that means the value of f of x1 is also less than f of x2. So if the value of f of x1 is also less than the value of f of x2.
But this condition will satisfy when we are approaching from a to b and b must be greater than a.
Yeah, so that's the meaning of interval. So whenever we write interval, this is the general convention, right? So a is less than b. So here, yeah, so a is less than x1 is less than equal to x2 is less than. So you can assume the same thing because that's the real line. So in the real line, we know that. So this is 0 and they're positive, and it's the basic real line. Okay. So if a function preserve this inequality, so that means if x1 less than x2, and then the value of function at x1 is also less than the value of function at x2, then we say that this function f is an increasing function in this particular interval. Increasing function in the open interval a comma. Right. So ultimately, so if x1 is less than x2, it should imply f of x1 is less than f of x2. So the inequality should present. Then we say that it is an increasing function. Now, what is a decreasing function? So if the value of x1 is less than x2, but the functional value is opposite. So that means, so if x1 is less than x2, implies f of x1 is greater than f of x2. Then in this case, what is happening? As we are increasing the value of x, the function value is actually decreasing, right? Here, what is happening? So here, if you are increasing the value of x, then the function value is also increasing, right? Such kind of behavior is there. This is f of x1 and this is f of x2. So in increasing case, we are some kind of preserving this inequality. So that means if you take x1 less than equal to x2, then the function value is also less than. That means f of x1 is less than f of x2. So
In
then
the
we say it is an
second
increasing
case, f
function.
of x is a decreasing function. The
So
interval
then
a
here
comma
we
b.
say, right, then f is a decreasing function in the same interval, open interval equal. Now, using this increasing and decreasing function, we can actually define what do we understand by turning points. Okay, so what is the definition of turning? So turning point is actually that point around which, if you consider the left hand side of that point, then the then the functional value is actually either increasing or decreasing, and over the right hand side the converse is happening. So what does that mean? So we have two scenarios. So suppose first scenario is this. So such kind of behavior is there. So this is a point x is equals to a, suppose. So that means at x is equals to a, it is a point a comma f of a. And this is a second scenario. So in second scenario, such kind of behavior is happening. Suppose this is f of a. So at this point, this particular point a comma f of a, what is happening? So in the first case, if you consider the left hand side of these points, then the function value is kind of decreasing, right? So here, decreasing behavior is there. And over the right hand side, if you observe, then the functional value is actually increasing. So such kind of points around which, around the left hand side, the function value is decreasing, and after that point, the function value is increasing. So such point is also known to be a turning point. Similarly, here also, same scenario happening, but in a reverse way. So that means here, over the left hand side, the function value is kind of increasing, and over the right hand side, the function value is kind of decreasing. Right? So such kind of points are known to be the turning points. Because here what is happening, the function value is actually turning, right? From the decreasing, we are going up to increasing after this point, right? And here also, the increasing behavior turning into decreasing behavior. So such kind of points are known to be the turning point. Okay, is there any doubt in turning point?
What about mod x?
So mod x, the turning point will be x is equals to 0. So this is the graph of mod x, right? Suppose this is origin. So here at x is equals to 0, what is happening? Around the left hand side, the value of function is kind of decreasing, right? And around the right hand side, the value of function is increasing. So that means this x is equals to 0 is a turning point. Is that clear?
No need this soft edge or sharp edge. No matters.
No, actually in turning point, it does not matter.
Okay, good.
Because turning point is what? So turning point is that point where the function is changing its behavior from either increasing to decreasing or decreasing to increasing.
Just getting it. Got it.
Right? Now let's talk about what will be the behavior of tangent at these turning points. Okay, so it's kind of very natural by the graph. So if you consider the graph where we have a turning point, so suppose this is some graph of function. So then we can easily judge by the graph that at this point, x is equals to a is a turning point, because what is happening from the left hand side, the function value is increasing, and over the right hand side, the function value is decreasing. So that means at this point, a comma f of a, function's behavior is changing from increasing to decreasing. So now this is a turning point. Now here, this function is smooth, that means it is a differentiable function. So here, if you draw a tangent at this particular point, then what will happen? This tangent, that means this tangent is actually parallel to the x-axis. So that means at turning point or at point of local maxima, again, this is a point of local maxima, right? So at local maxima, if the function is differentiable, that means we can draw a tangent there. So if we can draw a tangent, then that tangent is nothing but parallel to x-axis, right? And we know that if a tangent is parallel or a line is parallel to x-axis, then the slope of that line will be equal to
0.
0,
Zero.
right? So from that fact, we can simply say that if the function is differentiable, again, we are considering that function is differentiable here. So if the function f is differentiable at x is equals to a, and it is a point of either local maxima or minima, and it is a point of either local maxima or minima, then what is the conclusion? So then the derivative of function at that point is nothing but equal to 0. Now this is a pictorial proof, but this thing you can also prove by using the definition of derivative, right? So I am leaving that thing to you. But it's kind of obvious by seeing the graph that if you draw a tangent at a turning point or a point where we have local maxima or minima, the tangent is nothing but parallel to x-axis. Okay, is that fine?
Fine.
Now we can actually define what do we understand by a critical point. Okay, so now there is a very slight difference between critical point and turning. So this is the definition of critical.
Ma'am,
Okay, so what is a critical point? So a point x is equals to a is said to be a critical point of a function. Is a critical point of f of a function f. If two scenarios can happen here. So either the function is not differentiable if either f is not differentiable at x is equals to a, or f is differentiable and the derivative of f is equals to 0, or f is differentiable and if you compute f dash of a, that is equal to 0. So this is a thing about critical point. Okay, so critical point means, so any point x is equals to a is said to be a critical point of a function if the first condition is it is possible that f is not differentiable at x is equals to a, then all those points are also critical point. And the second condition is f is differentiable and the derivative at that particular point is nothing but 0. So this is a particular definition of critical point. Now, can we find out a relation between turning point and critical point? So the relation is that every turning point is a critical point, but the converse is not. Okay, so the relation is that every turning point.
Ma'am, please repeat.
The definition of critical point?
Yes, ma'am.
So critical point is, if you take any point x is equals to a, suppose you take any point x is equals to a, then this point is a critical point if one of the scenario is happening. So either this can happen or this can. So this is our definition. So if one of the property or one of the scenario happen, so what are the scenario? First thing is, it is possible that function is not differentiable at that point. So that point is also known to be a critical point. And the second thing is, if function is differentiable at that point, then the derivative should be equal to 0. So for example, consider, I'll give you example. So suppose again, we just look by the graph. So suppose you have this particular function. Suppose this is smooth. Okay. So here what is happening? Consider 2 points. 2 points means consider this point. So suppose this is x is equals to -2. And suppose this point, suppose this is x is equals to 5. Then what is happening at these 2 points? So at first point, what is happening? Is the function is differentiable here? Is f is differentiable?
No.
No, correct. Why? Because we have a sharp corner. We know that whenever we have sharp corner, the function is not differentiable. So that means here the function is not differentiable. And if you consider these 2 points, so suppose this point and this point, suppose this is x is equals to 1/2 or something. So here what is happening? The function is differentiable at these 2 points?
Yes.
Yes, it is differentiable at these 2 points because it is some kind of continuous or polynomial type of behavior, right? So we know that whenever the such kind of smooth behavior is there, we can say that function is differentiable. So here function is differentiable, but what is the value of derivative? So if you draw a tangent here, the tangent is also parallel to x-axis. If you draw a tangent here, the tangent is also parallel to x-axis. So that means at these 2 points, function is differentiable, but the value of function is 0, right? So here at these 2 points, what is happening? So that is at x is equals to -2, f is not differentiable. Right. At x is equals to 1/2 and x is equals to 5, f is differentiable. and the derivative is equal to 0. And f dash at 1 by 2. Similarly, f dash at 5, both derivatives are equal to 0. So by the definition, we can say that x is equals to -2, x is equals to 1 by 2, and x is equals to 5 are critical points. But in this example, what is happening? These are the critical point, but these are also turning points. Why they are turning point? Can someone explain? Okay, so I'll choose one by one.
Because-
So why this x is equals to -2 is turning point? Elengo, can you?
This function behavior gets changed, right? So
Right. So
it is increasing and decreasing at that point.
Right, correct. So that's why this is a turning point. Here also this is a turning point, and here also this is a turning point. But we can construct an example where this particular statement does not hold in the reverse direction. So for example, if I consider a function in this way, so suppose the domain is the whole real number. Okay, so suppose this is the function. Okay, so now observe this particular point. So that means this is a discontinuous function. So f is discontinuous. F is discontinuous. So suppose you have such kind of behavior. Here the function is discontinuous. Okay. So what is happening at x is equals to, suppose this is -1. This function is discontinuous at x is equals to -1. So since f is discontinuous at x is equals to -1, and what is happening, it's not so since it is discontinuous, can we say it is not differentiable? That's correct, right? So that means, so since f is not continuous here, so we can say that this will implies f is not differentiable at x is equals to -1. So by the critical points definition, we can say that x is equals to -1 is a critical point. Right? Because in critical point, we are gathering two type of point. First type of point is where the function is not differentiable, and second type of points are where the function is differentiable, but the derivative is 0. So is that clear why x is equals to -1 is a critical point?
Yes, ma'am.
Yeah, it is clear, right? So, but here what is happening? So if you consider the behavior of the function over the left-hand side of this point, then it is an increasing type of behavior. And over the right-hand side also, it is an increasing type of behavior. So that means at this point, the function behavior is not changing. So that means it is not changing from increasing to decreasing or decreasing to increasing. So that's why it's not a turning. So here, x is equals to -1 is a critical point, but not a turning point. Is that clear?
Ma'am, one very basic question. I mean, turning point and critical point is clear, but what is the, I mean, why are we even studying the critical point? I mean, turning point, I can understand that for the graph, the behavior at a point is necessary where we need to know where it's decreasing, increasing. But what's the use of studying the critical point?
See, actually,
turning
what
point
happened,
is not the critical
if the
point.
function is not differentiable at certain point, then it can happen that at that point we have the maximum value. For example, if you suppose you have a graph something like this, suppose it is something like this, here the value of function, and then here the value of function, and then here something like this. That means at these points the value of function are actually the function is not differentiable at these points. So suppose x is equals to -1, x is equals to -2. So here, if you compute the, if you want to look at the local maxima or minima, what do you say? So you'll say that there will be one point here, which is a point of local maxima, right? But what is happening here? So at these points also, function is taking the maximum, right? At these points, also we have the maximum. So such kind of scenario may happen. Can happen at non-differentiable points. So these points are some such type of points where the function is not differentiable, but function are taking maximum value at these points. So that's why it's better to include the function is not differentiable there. So one very good example is the example of f of x is equals to cube root of x. Okay, So if you consider this function, then we already observed that this function will look like something like this. Right? This is the behavior of function. Now here at x is equals to 0, we know that f is not differentiable. F is not differentiable at x is equals to 0. So because of this point, I mean, such kind of points are also critical points. But around 0, if you look any point, then function is differentiable at that. Here we just cannot draw a tangent because that tangent will be parallel to y-axis. So such kind of known to be a saddle point. So that's the two reasons we can say we are including non-differentiable points. So first reason is this reason, so it is possible that at those point function may take can take maximum value or some other values which are important for us. Another reason is this saddle point type of situation we always want to do. Because here, I don't think you guys are familiar with concave and convex behavior of function. But here function is changing from convex to concave. So that's why this point is also a point of interest for us. Okay.
Okay.
So these
So
are
just
the two reasons.
a follow-up question on this. So whenever
Mhm.
if there is a need to basically find the max or the min of a function that it can basically go to, then we basically consider all the turning points because it comes in under the continuous range of it. But then
Right.
we also make sure that we are also calculating separately the values at the critical point as well, making sure that it is not
Right.
exceeding what we have already calculated. So that, okay,
Right,
got it.
right.
Thank you.
So that's
And
the
critical points are crucial to understand how the graph behaves, and
right.
so
So
the
this convex
differentiation.
concave nature is
Mhm.
also related
Yes,
to critical
that is
points.
why it is important. Yeah.
Okay. Okay, so now one more definition, then that is saddle point. Okay. So what are the saddle points? So saddle points are those critical points where the function is neither taking maximum value nor minimum value. So you can say that saddle points are all those critical points which are not turning points, because we know that if a point is turning point, then it can be either maxima or minima. So what is a saddle point? So saddle point is that critical point. So it is a critical point which is not a local maxima, nor a minima. Okay, so one example here we can take. So if you consider f of x is equals to cube root of x, then we know that at x is equals to 0, the function f is not differentiable. Right? So since the function f is not differentiable at that point, we can imply that x is equals to 0 is a critical point. And at x is equals to 0, we can easily observe that it's not a point of maxima nor minima, because function is here also increasing. In the left hand side is also increasing, in the right hand side also increasing. So x is equals to 0 is not a point of local maxima or minimum. So we can say that x is equals to 0 is a saddle.
Okay. And the saddle points are basically used to filter out any calculation that we might have to do at the critical point. Is that the reason why the saddle points are now important? Because you said, right, that critical point can take the max or the min value of a function. But do we actually need to calculate the values at this point is the reason why we take the saddle point into consideration? Because saddle points won't hold any significance, right?
Right, that's correct.
Okay.
So you can say that, but so this is a one part, but the main significance of saddle points are this concave and convex nature of function, which you may learn in maths or somewhere else. But yeah, so the saddle points we can consider to be filter out the maximum and minimum critical points where we have maximum. Yes,
Okay.
that will be one solution.
All right. Thank you.
Ma'am, saddle points are used to find the maximum or minimum, local maximum or local minimum of f dash of
No.
x, right?
No. Saddle points are not, see, saddle points definition, what does it say? It say that we have to consider those critical point where the function is not taking function is not taking the maximum value nor the minimum value. So if it is not maxima and minima, how it could be what you're saying? Maxima
Ma'am,
and
we
F
can
minima.
dash
say
of
So
X, I'm telling, ma'am.
definition is that. Sorry, f dash of x. So f dash of x in this, since it's a critical point, obviously if the function is differentiable at that point, then f dash of x is equals to 0. Because again, we are involving in the definition the void critical point. And what are those critical points? So either it
No,
is
ma'am,
not
I'm not
differentiable.
telling, like, ma'am, in the lecture, sir has told that saddle points are
Okay.
used to point out the local maxima or local minimum of f dash of x, not f of
F
x.
of f dash of x. Okay, yeah.
Yes, ma'am. The other
This
meaning.
could be the case.
I hope I got. Did you understand
Right.
what I wanted to tell? Yes.
Yeah, so saddle points are also those points where f dash can have a local maxima or local minima.
Ma'am, can we define saddle point like
Yes.
this? A point which have a same behavior and it touches the x, then it's a saddle point.
It touches the what?
X axis.
No, it's not the case always, because if you shift this graph, what you can say, 1 unit upward and 1 unit toward the right hand side, then the saddle point will be something else, right? So this will be your saddle, which is actually not touching the x-axis. So this touching the x-axis, I don't think it's a necessary or sufficient condition for saddle points.
Okay, ma'am, got it.
Yeah. Right. So now let's now we will define what we can say the second derivative test for finding out the
The
maximum
point
and
of
minimum value.
inflection is also same as this. There is I studied something like
Point of inflection. Right.
It's same as saddle
It's same
point.
as saddle point.
Okay.
It's same as saddle point.
Wait, saddle points were the critical points, na?
Right.
So they should be
Saddle
turning.
points are critical.
So they should be turning point.
No. What do we say here? That every turning point is a critical point, right? So the converse is not true, no? So it's need not to be the turning. Every turning point is a critical point, but the converse is not true. That's we just observe by this particular example. So what is the statement? So this is the remark, you can say that every turning point is a critical point.
Okay.
But the converse is not true. Because although saddle point can never be turning point. Turning point means either it could be local maxima or local minimum. But in the definition, we are saying that it is neither of them. Right? Is that fine?
Someone was saying that first derivative function, something like that.
It will be, it can be the local maxima or local minima of derivative function. So that means we have two functions, f and f dash, right? So saddle point can be local maxima or minima of this f dash of x, not for f of x. Okay.
Okay. For the f, it will be the one that is not even local or maxima. Local maxima. Not, okay.
Not local minimum. Okay. So now let's go to the second derivative test. So second derivative test will help us to find out what are the point of local maxima, local minima. Using the, obviously it uses the second derivative. So the second. Okay, so what does it say? So it says, again, since we are using derivatives, we have to assume that f is differentiable. Okay, so suppose f is differentiable. And we are assuming that f dash and f double dash are both exist at the point x is equals to a. Then first what we do, we will get the critical point by using f dash at a is equals to 0. So the first step will be find all those points, find the critical points. Using this particular equation, f dash at x is equals to 0. So if you use this equation, you will get all critical points. Then second thing, so suppose if we have a critical point, so suppose x is equals to a is a critical point. Then we will look the sign of second derivative at this particular x is equals to. So then there are two cases. So first case is if the second derivative at A is strictly greater than 0, then the point x is equals to A is a point of local minimum. Okay, so if it is f double dash at A is greater than 0, then it is a point of local minimum. Okay. Now, if f double dash at A is less than 0, so the second case will be, so suppose if f double dash at A is less than 0, then this point x is equals to A is a point of local maximum. Okay, so if x is equals to A is, the second derivative at A is strictly less than 0, then it is a point of local maxima. And the third statement says that if double dash at A is equals to 0, then actually our test will fail. So here we don't get any confusion. Okay. So this is the second derivative test. I think you guys are already familiar. Is there any doubt in this particular test? How we proceed? First, we find out all critical points and then look the sign.
Ma'am, I do have one question though. So yeah, this equation I'm aware of, that if double dash A is greater than 0, then it's a minima. But is there any reference where I could essentially find out why f dash,
Okay.
f double dash A is
Right.
0 is to be considered as
So
a
the
minimum?
proof you're asking, right? So proof
So
of the
just from
second
the
derivative
graphical
test.
point of view, because when you drew the graph, right? So at any point which is a maxima or a minima, we know that if we draw a tangent, essentially the rate of change is constant. So that's why f dash A is equal to 0. But the
Right.
double derivative of that tangent, how does it conclude that if it is a positive, then it is a max, and if it's negative, then the other way around.
Okay, so for doing that, we have to observe one relation between f dash. So I think you are familiar with this, I don't know. So suppose you have a differential function. So suppose f is differentiable. And if we have any open interval a comma b, and in this open interval, if the sign of f dash is strictly greater than 0, then you can say that f is an increasing function in this particular interval, open interval. Is this fact is fine for you? So if that sign of derivative actually tell us the increasing decreasing.
Correct.
Okay. So here what happens? So what is so here we are observing the increasing and decreasing behavior of f dash using f double dash. So that means if f double dash at x is strictly greater than 0, this will implies that f dash is an increasing. Yes, Aditya. Okay. So if f double dash of x is strictly greater than 0, then we can say that f dash is an increasing. Now, if we consider this local maxima or local minima type of behavior, I'm actually not sure if can we go along this. Then here the value is actually decreasing. So if you consider the slope of tangents, then the slope of the behavior of f dash is kind of increasing in this way and decreasing in this particular part. But
That is correct. That is correct.
Can we use this to conclude f double dash? No, actually, I forgot how to relate
F dash
this.
is decreasing, right, ma'am?
F dash is decreasing here, and f dash is increasing here. F dash is 0 here. So we have to relate this scenario with this thing. F double dash of x is less than 0. So if f double dash is less than 0, what does it mean? So it means that f dash is decreasing in this particular phase. This is not actually correct. This particular representation is not correct. I'll let you know. Actually, I'm also.
Yeah, ma'am. That is fine.
But we use
All I
this
want
fact.
is a reference. Like if you have like some reference to any books or any
I think
site.
Thomas calculus involved the proof.
Okay.
Thomas
Alright.
calculus.
I think this information available in the lecture. If you okay means I can explain that point. Madam, if you okay, can I explain?
Yeah, sure.
Yeah, that graph you draw, madam, can you undo that one? So in this I can explain because I saw in lecture.
This one?
Okay, yeah. So what they are telling in the lecture, if you are doing the first derivative, we'll get the point where the critical points, right? So
Right.
this critical point is denotes the y value. So when you second derivative, when you apply that point, the exact below x-axis point is we are getting.
Means?
So this point, no, this related to that point, exactly this point graph is traveling, second derivative. So I hope if you if you graph the things now after the second derivative, that is passing through this particular x-axis line. You are drawn on a vertical right in x-axis. That particular axis is going that curve. I hope I answered.
Yeah, I kind of get an idea. But anyways, I'll look into the visual proof of it. But thank you. I kind of got an idea of what you're trying to say.
Yeah. So what is the first point? This is the graph. Then the second derivative, if you put the graphing tool now, so you can understand the exact that particular point is traveling the curve.
Okay. Okay, I'll take a look at the visual proof graph. But thank you. I don't want to derail the conversation, but yeah, you can move ahead.
Yeah, you can check. Although we can discuss in the next tomorrow session also. There also I can take 5 minutes to explain this. Actually, I forgot how to relate.
It is, ma'am. No, it is nothing. So when you are getting f double dash of x, it is greater than 0. The concave is, it is like. I mean, the slope is getting increased. So then that is the reason. Yeah. So that is the reason it is local minima. Either way, it is around. When you are getting, it is f double dash of x is less than 0, then the slope is getting decreased. So that is the reason it is.
So that's why it's
yes, correct.
Double dash x. So just is it strictly increasing or strictly decreasing?
We cannot say strictly because we can say if it is strictly greater than 0, then you can say strictly increasing. Because if it is a constant, then derivative will become 0. So yes, you can say strictly increasing with respect to strictly greater than 0. Right? Okay. So is there any doubt in local maxima, minima, saddle point, critical point? All definitions are clear, right?
Yes, ma'am.
Okay. So now same thing we can do with the closed interval. If we have a function defined in a closed interval, then also we can apply the same result to find out the critical point and to find out the local maxima and minima. But in closed interval, what happens? So suppose you have a function. Suppose f is a function in a closed interval a and b. Then one additional task you have to do, that you have to also look at the endpoints. That means look at the points a comma f of a and b comma f of b also. To find out it is possible that these points could be the local maxima. For example, if you have such kind of parabola from suppose this is some x is equals to -2 to x is equals to 4. Suppose this is a one parabola, then what is happening? At these two endpoints, we are getting the maximum value. So if we have a function in closed interval, then we have to check the value of function at the endpoints of the interval. Okay, is that fine? Just one remark you can say. Now using local maxima, local minima, we can actually find out global maxima and global minima. So what are the global maxima and global minima? So global maxima is the maximum among all the local maxima. So suppose you have a function like this. Right. So here you observe that we have so many maximum values. So suppose x is equals to, suppose -2 is there. This is x is equals to 2 is there. X is equals to 5 is there. Right. So here what is happening? These 3 points are local maximum. But at x is equals to 5, we are getting the global maximum. That means if you consider this to be a function from real number to real number, and suppose this is also decreasing to infinity, this is also going to -infinity. Okay. Then what is happening? This is a point where we can say that f of 5 is actually greater than equal to f of x for all x belongs to real, not a small neighborhood, but for the entire domain. So such kind of maximum value is going to be the global maximum. right? The word global means it is a maximum, it attain maximum over the whole domain, not a specific interval. Okay, so that's the one term, global maximum. And similarly, we can define what do we understand by global minimum. Is that fine? This whole part, maximum, minimum.
Is this the global maxima is also called absolute maxima, or that is a different term, ma'am, or both are same?
Absolute maxima, I think it can call, but I'm not sure about this term.
Okay, it's fine.
We use this global so many times.
Yeah, and all this value, ma'am, we need to apply it in the f of x only. Correct, ma'am, to find that the point, right? It is not in the f dash.
Right.
Okay.
No, f of x only, because they are the maximum minimum value of function f, not f dash.
Okay, ma'am.
So, okay, so we will discuss some of the examples from the practice or activity question in the next session. For now, the theory part is clear. Okay, is there any doubt in the theory part? Okay, now let's go to the area of a curve or area of any region. So suppose you have the computation of area is a very basic problem, right? So if you have any region, so suppose you have a region, something like this, right? So this is a particular region and this shape is known to us. That's nothing but a rectangle. And we know that if we have a square, then what is the area of square? So suppose, assume that this is a square of length L. Then the area of square, we know that, then the area of square is what? L square, right? So this is the area. Now, using this squares area, we can actually compute the area of rectangle, right? How we can compute? We will just divide this rectangle into squares and then we will compute. So if we have such kind of abstract figure, so that means these are very simple figure. The boundaries are nothing but straight lines. So suppose you have a triangle, or if you have a right angle triangle, or anything, any figure which can be deformed into squares, right? So we can actually find out the areas of such kind of figure by just doing some kind of adjustment in the area of triangles or area of squares, right? But what happens if we have a very unnatural figure? So suppose you have such kind of figure. Now, how do you compute the area of such kind of figure? Right? So that's the main question. So now this question we can answer by using the integration process. So what is the integration? So integration is actually the first time if someone evolved the integration process was the Riemann. So what does Riemann did? So he divided this particular region into small rectangle strips. And then they say if you divide it in very fine rectangle strips, then the area of those rectangles, that means addition of area of those rectangles, will be some kind of bound this particular area. So suppose we can understand this by a figure. So suppose we consider a very small, very basic function. So this is one exponential function, you guys already know. So here, if I want to compute the area between these lines, so suppose x is equals to 0 is my line, and x is equals to 5 is my line. So these are two lines. So that means I want to compute the area bounded by these four lines or four curves, right? So this is y is equals to 0 line, x is equals to 0, x is equals to 5, and then this function. Then how we can compute such kind of area? So what does Riemann say? So Riemann says that divide this area into small rectangular strips. Okay, so we can divide in rectangular strips. Now, in a rectangle, we have two things. We can measure the height, we can measure the breadth, right? So here, the what we can say, the breadth or whatever this is, width, breadth, whatever you say. So this is nothing but a distance between two x points. So suppose this is x is equals to 0, and here if I assume that x is equals to 0.5, then the value of b here, then the value of b is nothing but 0.5 minus 0. So that means we can actually define the rectangle of breadth something like this. That means difference of two x values. But what about the height? So for height, we have so many choices, right? So one can say that, okay, you can take this point and make the value here, and whatever value here is, that means you can take f of 0.5 to be your height of rectangle, or you can take f of 0 to be the height of your rectangle. Okay, so that means for
f of
height,
1, 2,
we
3,
have,
anything.
yeah. So that means among this particular interval, you can choose any point, any f of xi, you can choose and say that this is the height of rectangle. So here for height, we have a choice. right? So because of this choice, we have three type of Riemann sum: the left Riemann sum, right Riemann sum, and middle Riemann sum. But in our course, we generally define only what is the Riemann sum, and then what is the definition of integration. Okay. So what does Riemann says? Okay, you can choose any height, and based on that height, if you calculate the sum of area of all those rectangles, and if as you find all these rectangles, so that means as you take as you increase the number of rectangle in your particular area, then this particular area should be converged to something. Converge means, again, we are using limiting behavior here. What we are doing, we are finding the breadth of rectangle. So that means we are taking, suppose this breadth is delta x, then we are saying that delta x goes to 0. So as we find our breadth of the rectangles, then the area of this particular, then the area sum of all the rectangles will some kind of give us a very good approximation what is the whole area is. Okay, so that's the main idea behind the Riemann sum. Now, how do we do this? All the stuff, whatever we say here, how do we mathematically write this? Okay, so one thing is here, for choosing the rectangle's breadth, we have to consider some points, right? And those points are nothing but a point between x is equals to 0 and x is equals to 5, right? So for dealing with these points, we define what do we understand by partition. So what is a partition? So partition of any closed interval. So this is also known to be a, partition of any closed interval, we can say. So it's actually a set of finitely many points between that. So let P be a, can define what do we understand by partition. So this partition we are using for dealing with this breadth type of situation. Okay. So a partition of any closed interval a comma b is a set of finitely many elements, of finite elements, of finite elements, or you can say numbers, in such a way that you have to choose finitely many numbers in between a and b in an increasing order. So that means you can choose your first number x0 to be equal to a, then you can choose your second number to be x1, which is strictly greater than x0, and you can choose the third number to be x2, and then so on, right? And you can choose the last number to be your b. Okay, so then if you consider the set of all those points, that means x0, x1, and so on, xn, then this is your partition P of closed interval A. Now here also we have choices. You can choose any type of number or any x0, x1, x2, x3, depending on your choice. Okay, so this is known to be a partition of a closed interval AD, closed interval AD. And why do we need this partition? Because again, what is our main idea? So main idea is to divide our area into rectangle strip. And if we have a rectangle, we have two type of things. So first is this particular base or breadth, you can say. So we want to know what we can choose in terms of breadth. And the second thing is the height. Okay, so for this particular thing, that how we can choose our breadth and how we can increase the number of rectangle in particular region, we uses the term known to be a partition. Again, what is a partition? Partition is nothing but a collection of finitely many points in between A and B, but in increasing order. So that means x0 should be less than x1, should be less than x2, should be less than x3, and so on should be less than x. Okay, so this is known to be a partition. Now, with this partition, we actually define the norm of partition. Norm of partition means we define a value norm of P. And what is this norm of P? So if you consider the distance between all points, so that means if you consider this distance, that means x1 minus x0 and name it to be delta x1. And if you consider the distance here, so that means x2 minus x1 and name it to be delta x2, and so on. So if you consider the distance between every two points, then among those all distance, if you consider the maximum distance, so what we have to do, we have to consider the max of delta x1, delta x2, and so on, delta x. So whatever this number is known to be the norm of partition. Now, what is this partition is actually doing? So this partition actually dividing your closed interval AB into n subintervals. So that means, so this is our closed interval AB. This is A, this is B. Then we are choosing some points here. So this is our x0, this is x1, this is x2, this is x3, up to and so on, xn. Sorry, xn minus 1, and this is your x. So what is this partition doing? So this partition is actually subdividing the enclosed interval AB into n subintervals, right? So this is one subinterval, right? This is your second subinterval. Similarly, this is your third subinterval. And at the end, we have the n subinterval. Nth subinterval. And what is this norm? So this norm says, if you compute the length of each subinterval, so we know that what is the length of this interval, this subinterval is x1 minus x2. This is our del x. The norm of this, the length of this particular subinterval is x2 minus x1, which is equal to delta x2. And so on. The length of the subinterval is xn minus 1, which we are denoting by delta x. So this delta xn is nothing but a number which gives us the length of this particular subinterval. So if you choose the largest length, that length is nothing but norm of. Okay. So is that clear? The definition of partition and the norm.
Ma'am, could you please repeat what partition is used?
What partition
To
is?
What partition is basically used to divide our interval into very minute rectangles.
Very right. So here you observe that if you apply the limiting criteria that norm p goes to 0, then what does this particular limit will do? It will increase the number of rectangles in our particular figure, right? So norm p goes to 0 means we are treating this particular delta n goes to 0, right, for some I. So that means this breadth, whatever the breadth we are taking for rectangle, this is actually becoming very finer in. So this limit we can now apply to say that, okay, if we apply this particular limit, norm p goes to 0, then the breadth of our rectangle will become very small, and very small, up to 0. So that's the main purpose for defining partition.
If we partition, it would be always the same size, no? Then the delta would be same only, right, ma'am? Then how are you getting the maximum of the delta?
No, it need not to be always the same. So for example, if you consider this, suppose we have a closed interval 0, 1, and if I divide this interval into 3 parts, but what are the 3 parts? So here, let me take
1 to 3.
3 parts. So suppose 1 by 2 is there and 1 by 3 is there, and then what is the length of this interval? So this interval will have length 1 by 3. This interval will have length 1 by 3, I guess only, right? And this whole interval will have length 1 by 2. This is 1 by 2, I guess 1 by 6. So here what is happening? The delta x's are different, right? So this is your delta x1, this is your delta x2, and this is your delta x3. So here delta x1 is 1 by 3, delta x2 is 1 by 6, which is again 1 by 2 minus 1 by 3. Okay. And delta x3 is equals to 1. So it depends. So if you want to divide your partition, if you want to divide your interval, closed interval AB into equal parts, then obviously this delta xi will be same. But it is possible that we want to divide into some unnatural type of distribution. Whereas we never use such kind of distribution, we always divide the partition into equal parts. But yeah, it's better to know what can happen.
Okay.
Right? Yeah. So because this is also one kind of partition. So it's not always the case that delta xi's are all the same, but we in general take these to be, the subintervals to be of equal length. We don't want them to be unequal length or some kind of thing, right? Okay, so is this scenario is okay that what we want to do, we want to increase the number of rectangle in our particular area so that we can get a good approximation. So this problem is solved by taking norm p is equals to 0. Okay, so if we apply this particular limit, we can actually resolve this issue. That we can actually consider infinitely or so many rectangles in so many fine rectangles in this particular area. Now we also want to resolve the issue of height. So what are the point we can choose? So here the thing is, you can actually choose any point to be any point xi to be your yeah. So this width isn't defined for 0. Yeah, so that's why we are taking limit norm p goes to 0, not direct norm p equals to 0. Because if the norm p equals to 0, that means we are taking only straight line. We don't want straight line, we want very fine rectangles. So that's why we are taking norm p goes to 0. Okay.
Indirectly we can say very, very small rectangles of width.
Very small rectangles. Now for height, actually Riemann gives us a freedom that you can choose any point in between your subintervals. So that means, suppose you have a partition. Suppose you have a partition P to be equal to x0, x1 up to xn. Then we have one rectangle, right? So we have one rectangle whose what you can say width will be equal to, suppose this is your x0 and this is your x1. So this width is nothing but x1 minus x0, and this is the height. So now for the height, you can choose any point xi, or you can say that this point is actually denoted by x1 star. Okay, so this is x1 star. Any point you can choose in between x0 and x1 for your height. So that means you can choose height to be equal to f of x1 star for any x1. For any x1 star belongs to open interval x0 comma x1. Or you can say close interval x0 comma x1. You can choose height to be equal to x0, or you can choose height to be equal to x1, or any point in between these particular rectangles. So now what will be the area of this particular rectangle strip? So now the area of one rectangle strip.
Ma'am, could you please repeat
Exact.
how we take a height?
Yeah, so for height, actually, we have a freedom to take any point in between x0 and x1. So we have a freedom, you can choose any point. It doesn't matter, it can be equal to x0, it can be equal to x1, it can be equal to any point in between them. So suppose you divide close interval 0 to 1 to in between, two subintervals. So here in place of height, you can choose any point. You can choose x is equals to 1 by 4, x is equals to 1 by 3. Any point you can choose. That's the freedom we have. That for height, we can choose any point which lies in between this particular subinterval x0 and x1. Okay. Is that fine?
Ma'am, so
Ma'am,
Yes,
he is
Rahul.
asking why we can take this height.
So actually what happened, based on this height, we have three type of Riemann sum, which is, I don't think in our course we just have one type of Riemann sum, but this is one extra information you can say. So by this particular height, we actually have three type of Riemann sum. So if you take if you take your height to be equal to f of x0, then this is known to be the left Riemann sum. If you take height to be equal to f of x1, then this is known to be the right Riemann sum. And if you take height to be equal to x0 plus x1 by 2, then this is named to be the mid Riemann sum. And actually what happened, if your function is integrable, what do we understand by integrability? That also we will take. But if you take any, if your function is integrable, so then what happened? All these areas will converge to one particular thing. So the reason we can take any point is that if you consider the very small fine rectangle, so here if you consider norm P goes to 0, then if you choose any point in between this particular small thing, then all points some sort of get collide with each other, right? So ultimately that's the reason you can say, because we have a very fine strip, so there is not much difference if you choose any point in between these two intervals.
Can we say that we are doing integration according to the function? So obviously the function has my slope. So can we say that my graph will behave according to my function slope? So no need to worry about the height.
No, that's the because see, here we have a very nice function, right? So what's your point? Can you repeat once again?
No. If, for example, this x plus 1, y equal to x plus 1, that is my function. So from 0 to 3, I want to calculate the area. So obviously, the rectangle I can fit as I have a slope of 1.
Rectangle fit as slope of 1 means?
No.
This is your rectangle, right? This is your
Okay.
y is equals to
That
x plus 1.
yeah. So
X is equals to
he's
0.
asking about the height of the rectangle. So rectangle height we are not considering here. in the Riemann sum.
Yeah,
So
we
as
have.
we know, the slope of the function is 1, x. Okay, so that we are doing integration in that particular slope on my function, so that we can say that we don't need to worry about the rectangle. Or I don't know.
I'm not sure about this because see, one thing is we are not worrying about the height is that we are ultimately taking norm p goes to 0, right? So when norm p goes to 0 means all the points are very close to each other. So if you consider this small interval x0 to x1, then as norm p goes to 0, this interval will get shrunk again, right? It will be again small interval, again small interval. So ultimately it actually doesn't matter whatever point we take as our height, because the change in the height will be very small. So that's the one reason you can see.
Yes, ma'am.
But
Because
breadth is okay.
taking very small.
Height is concerned.
Yep. In the small width, the height doesn't fluctuates that much.
Height doesn't matter, right? Because our rectangle will become very fine, very fine. I mean, something like this. So here doesn't matter, you will take height this or this or this, right? So as norm p goes to 0, it will take care of this particular height. Is it clear? Are you getting the intuition?
Yes, okay, no, fine.
Fine for everyone? Any doubt?
Madam, all three options, it will give same answer only, right? Left, right, and
if
mid.
the function is integrable, so we define that if such kind of limit exists, then we say that function is integrable. And if the function is integrable, no matter whatever height you will choose, it will converge to one particular thing.
Okay, so if you want to take left, then x0 we need to take as a height, and if you are taking r, then we need to take x1 as a height.
Height, right?
Then midpoint, how you will select actually x0 plus x1? How we can select the midpoint?
Midpoint means average of this particular interval. So suppose you have interval from 0 to 1, then midpoint will be 1 by 2, right? So in midpoint you will take x0 plus x1 by 2, average. Average of these 2 points.
No, now if you are dividing to the more division, then I will take midpoint actually. So
so if yeah, so then we actually after doing the summation we will take limit. So I'll come to that. Okay. So just one second.
All
Sorry,
rectangles
ma'am,
are
but I
different.
got a very little idea.
Yes, sir.
Ma'am, actually, I got a very little idea about the heights. Very sorry, I didn't able to catch that. Could you please explain like a more brief example? Is it about time bound or not?
See, what happened? What we are doing, we are actually finding our width of the rectangle. So if you consider a rectangle with such a small width, suppose this is your rectangle, then then the function will behave like here. Suppose this is our function, right? So what we are saying that we can take any point to be our height in between such a point, right? So here what is happening? The values of function are very close to each other, right? So that means here doesn't matter
Yes,
you will
ma'am.
take f of x0 to be your height. Doesn't matter if you take f of x1 to be your height, or if you take any midpoint of that, f of x0 plus f of x1 by 2, because all these quantities are very close to each other. So that's the one reason. And also we are taking norm p goes to 0. Norm p goes to 0 means we are finding our rectangle much, we are finding our rectangle up to the 0th, very small quantity you can see. So the rectangle will ultimately look like a straight line. So here we have here the functional values are very close to each other. So that's the one reason you can take height to be any two. Because ultimately we are shrinking our rectangle, right? So as we shrink our rectangle, no matter whatever height, no matter whatever function value it is, they all will be very close to each other. Is that fine?
Okay, ma'am. Okay, ma'am.
Okay. If not, then let's think about it, because this Riemann integration is. So suppose for time being, suppose you can take any height. Okay, so suppose for a subinterval x0, x1, I'm starting with the first subinterval. So suppose we have, this is our first subinterval. So for this particular subinterval, what is our width? right? So here width is nothing but delta x1, which is x1 minus x0. What is the height? So height is, we can choose any x1 star. So we can choose any x1 star belongs to close interval x0 comma x1. And that f of x1 star we can choose to be our height. Then what will be the area of this first rectangle? Area of first rectangle. So the area of first rectangle will be multiplication of height into width, right? So that means f of x1 star multiplied with delta x. So this is the area of first rectangle. Now what we have to do, we have to sum all those areas. So if you do sum, so then this is known to be the Riemann sum. And suppose you are dividing your subinterval into n points. So suppose the cardinality of our point, it's not complicated. So suppose we are dividing our closed interval a comma b into n subintervals. Then this Sn is nothing but the sum of all those areas. So here area will be xi star into delta xi, where I is ranging from 0 to f. Okay, so what we are doing, we are taking sum of area of all rectangles, right? So here you observe that this is the area of first rectangle. Similarly, if you consider the area of second rectangle, so the area of second rectangle will become f of x2 star into delta x2. So this is the sum of areas of n rectangles. Is that fine? This particular sum?
It is the value of the function.
F of xi star is the value of function.
Yes.
So this is the sum. Now what we want to do, we want to apply this particular limit, that norm p goes to 0. What is norm p? Norm p is the maximum length, or you can say delta x. So as norm p goes to 0, we can actually say that we are actually increasing the number of points in our particular partition. So that means as norm p goes to 0, we can say that n goes to infinity. Because as norm p goes to 0 means we are actually increasing the point in our particular partition. So suppose this is the original partition x1, x2, x3, x4, x5. Then if I introduce one more point here, then what will become? The length of this particular interval will divide into 2. If I introduce one more point here, so by introducing much more points, we can actually consider this particular limit, norm p goes to 0. So which means that this limit norm p goes to 0 is same as n goes to infinity. So that's why if you apply here, so we can say that if limit n goes to infinity Sn, so that means this particular limit n goes to infinity of summation I is ranging from 0 to n, the area of all rectangles xi star delta xi. This limit, so if this limit exists, we can say that our function f is integral. Okay, is that clear? That's the definition of integration. It's something we are deriving. It's a definition of integrable. So that means this is how the integration of any function defined initially. At the starting or at the very starting of integration theory, that's the first definition. How we can say that a function is integrable or not. As for the differentiability, we consider one particular limit, right? So similarly, integration is also nothing but a limit of some of the areas of all rectangles.
Madam, what is that? F is, what is that? Integration.
Integrable.
Integrable. Okay.
Yeah. Okay. Is that fine?
Yes, ma'am. Okay.
Okay. So if you're not got it, it's just the theoretical part, just a motivation, or you can say a theory of how the integration come into picture, right? How the differentiation come into picture, that's also we understand. So this is the thing, that what is the starting point of integration in maths. So that's how first Riemann defines some integration. Then actually what happened, there are so many clauses, and so not so many, there are particularly 3 clauses in this integration. So if you are interested, then you can study further. But that's the starting point of integration of any function. So if this particular limit exists, then we say that function is integrable. And it's actually very tough to show that a function is integrable using this particular Riemann definition. So that's why we never bother about a function is integrable or not. We know that we have one result. That result says that every continuous function is integrable. Every continuous function is integrable. So we always uses this particular thing that, okay, if a function is continuous, it will be integrable. So that means this whole complex limit will exist. So we don't have to bother about, first we have to partition and then compute the area of each rectangle and then find the limit. So it's a very hectic process. We don't always, I mean, in our course, we never prove a function is integrable or not. There will be, I think, one or two examples, but those examples are will be of either linear function, right? I think there will be some example in practice assignment which are linear function, and there you have to prove this Riemann sum exists or not, something like this. But in general, for a complex function or for quadratic or cubic function also. Yes.
Ma'am, converse is true.
No, the converse is actually not true, that every continuous function is integrable. This is true, but the converse is not true. For that, we need some other there is one example that is very abstract. So for timing, you can consider that, okay, converse is not. It is not always the case that if you have an integrable function, that it will be continuous.
So from here, ma'am, we can
Yes,
say that the previous graph which you have drawn, you are trying to identify the area of the portion. This portion, we can say integral a dot dx. This is the
right. So the integration of this particular region will become, now here this limit is actually denoted by integration a to b. So this limit, okay. So this limit is actually equal to integration a to b f of x dx.
Because remembering all those things is quite complicated.
Right. Yeah, you don't have to remember all those things, how we actually come to integration. It's just for your motivation, so that since you know the integration, so you should know how it comes into picture or how it actually defined, right? So this is just for giving you a feel of integration, that how integration or the theory of integration started. Okay, so this area is actually.
So ma'am, from here we can say integration is nothing but all the points in the interval. If we sum all the points, then we can get
all the areas, rectangle area.
All the rectangle areas.
That thing you can say. And this result we always use, that every continuous function is integrable, but the converse is actually not true. For that, you need some other type of example. Okay. So now this limit is denoted by integration a to b f of x dx. Okay, is that fine?
Yes, ma'am.
Now we actually compute the integral, or this is known to be the definite integral, using the antiderivative type of thing and the fundamental theorem of calculus. Okay, so what does fundamental theorem of calculus do? It actually relates this particular definite integral with the process of differentiation. So that means fundamental theorem of calculus, that this thing I will define later. So first talk about the antiderivative. So what is the antiderivative? So antiderivative is nothing but a function whose derivative is this particular small x. So what is an antiderivative? So in MT, derivative of a function small f is another function capital F, is a function capital F whose derivative is actually the small f. This derivative, so that means f dash of x is equals to small. Then this particular capital F is known to be the antiderivative of small, right? So derivative means differentiation. Antiderivative means whose derivative is this particular small f. So whatever the function is here, this function capital F is the antiderivative, is a antiderivative of this particular small f. And why I'm saying a antiderivative, because here you observe, if you consider two functions, so suppose you have two functions, suppose capital F1, you can take simply x plus 3. In capital F2, you can take simply x plus 5. Right? So here quite obvious that F1 is not equal to F2. Capital F1 is not equals to capital F2. But if you consider f1 dash, so what is your f1 dash of x? It's actually equal to 1. And this is same as f2 dash of x. Right? So if you consider small f to be equal to L, so then if the small f of x is equals to one constant function, then both f1 and f2 are antiderivatives of this one. Then both capital F1, capital F2 are antiderivatives of the small f function, right? So that's why antiderivative is not unique, but they only differ by a constant. So that means here you observe that the constant is different. And why they differ by a constant? Because the derivative of any constant will become 0. So that's the fact here. So if someone asks you that antiderivatives are unique or not, so they are not unique, but they only differ by a constant term. Okay, is that fine? Now, what does fundamental theorem of calculus do? It actually relates the definite integral. So that means whatever complex process we have discussed so far, that complex process we can actually relate with differentiation. So how does it relate? So that's why it's known to be the fundamental theorem of calculus, because it gives a very nice relation between one complex thing and one very easy property of function, right? So fundamental theorem of calculus. So what does it say? So it says that suppose, again, we want integrability. So that's why we are assuming the continuous function. So suppose f is continuous on some domain, any domain you can say, on some domain T, or we can take closed interval in place of that. So suppose f is continuous on closed interval AB, and let capital F be the antiderivative, be the antiderivative of the small f. Of the small f, then the integration, that means the definite integration a to b f of x dx, this is nothing but the capital F of b minus capital F. Antiderivative of small f means, so that is capital F dash is equals to small f. So here you observe that this is a very small thing, right? So we just have to use, this is nothing but we can compute it by using differentiation. But this involves a very long process of Riemann sum and Riemann limit and all those things. So this is a definite integral. So here this fundamental theorem of calculus actually related to one difficult thing to one very easy thing, that's the differentiation. And this is a relation between integration and differentiation. So if you consider the integration a to b f of x dx, this is same as f of b minus f of a. Where what is this capital F? This capital F is nothing but antiderivative of this particular small. Okay, is that clear?
Yes.
This antiderivative part is quite unclear.
An example.
So antiderivative, see, what is the derivative of function? So if f is a function, so if f is a function, then you have to differentiate it, and whatever function you will get, that is a derivative, right? So this is the derivative. Now, what is antiderivative? Antiderivative means you have to find a function whose differentiation is this particular small f. So that means in place of here, we have small f, and in place of here, we have a capital F. So we want to find a function f whose derivative is this particular f. So that means f dash is equals to small f. So for example, if you consider a function, so suppose you have a function f of x to be equal to x square plus 2. Now, what you can say, what will be the antiderivative of it? So what is the antiderivative? So antiderivative is that function capital F in such a way that capital F dash is equals to small f. So that means we want to find out a function capital F in such a way that capital F dash of x is equals to small f of x, which is equals to x square by 2. That means capital F dash of x is equals to x square by 2. Now what are the guesses we can say? Okay, since x square is there, so if I differentiate x cube, I can get x square. But right, so that means if you differentiate x cube, you will get 3x square. But here we don't have 3, so that means we have to take 1 by 3 here also. So if you differentiate 1 by 3 x cube, then you will get x square. And for 2, if you differentiate if you differentiate x, you will get 1. But since we want 2 here, so if you differentiate 2x, you will get 2. So that means we can take capital F of x to be equal to x cubed by 3 and plus 2x. Now here, if you differentiate this particular capital F of x, what you will get? You will get 3x square by 3 and plus 2, which is x square by 2 and which is equals to small. So that's the little difference. So antiderivative means you have to find that function whose derivative is this particular small f. And derivative means just differentiate this small f. Is that fine?
Yes, ma'am.
Clear? Everything? Any
Clear.
doubt?
Yes,
In that x cubed by
Yes, sir.
3 you written plus 2x you written. After what did you do? 3x
See, here
square.
so here actually I want to make a guess that how I can get a function whose derivative is this x square by 2, right? So we know that if you differentiate x cube, you will get 3x square. But here we just have x square, right? Here we just have x square. So I'll just make a little adjustment of 1 by 3. So if you differentiate 1 by 3 x cube, then you will get x square. Correct? Because derivative will become 3x square by 3. So that's why x square. This is the little adjustment I have.
Plus 2x, right? So you put 2.
So here also, if you differentiate x, then you will get 1. But if you differentiate 2x, you will get 2.
Yeah, that I
Right?
know. Yes.
So that's why if I differentiate now the sum of these two quantities, that means x cubed by 3 plus 2x, I will get x square plus 2. And this is our small. So this whole function I can consider my capital, whose derivative is the small.
Okay, ma'am. So
Is
the
that
answer will be
fine?
x cubed by 3 plus 2x, right?
Plus 2x. But you don't have to do it via this particular guessing. We actually have fundamental theorem of calculus. We just kind of integrate it. So that's the next thing I want to say.
What
So
about
the
the
second part
constant
of
then?
constant then means?
Constant means we are negating the constant, right? When you are
So
doing
here,
derivative, what will you do?
Here also you can consider plus c. So you can
That
consider
is
plus
what.
c. Right.
Okay. Then one will be find this c. The c will be remain same or what?
This c is actually it depend on the scenario. So if you have some condition which will give us a particular fixed c, then the antiderivative will be unique. Otherwise, that's why we say that the antiderivative is not unique. We have a antiderivative, not the antiderivative, because every antiderivative of function differ by a constant. This constant is this c.
Okay. He was saying an antiderivative, not the I don't understand in the lecture when we're watching. What is that?
Okay.
This is
So
wrong.
see, we have n antiderivative, right? N antiderivative, n antiderivative means it is possible that we can find out for a one function small f, we can actually find out so many antiderivatives, capital F1, capital F2, capital F3, up to so on. So suppose one example I have did that if you consider f of x to be equal to x plus 2, then you can consider your antiderivative, or simply let's take constant. So suppose you have a function f of x is equals to 2, then if you consider your first antiderivative f1 of x to be equal to 2x plus 1, right? So if you consider this f1, then also you will get f1 dash is equals to 2, which is equals to your square. But here if you consider f2 of x is equals to 2x plus 2 also, then also you will get f2 dash is same as 2, which is equals to square. So that means here for one function, we are getting so many antiderivatives. But the only difference between all those antiderivative are just a constant, right? This constant is c. So that's why we say an antiderivative, not the antiderivative.
Okay.
Because the means unique, right?
Only one, yeah. Okay.
Ma'am,
Yes,
does Madhav's statement is right that every linear functions are antiderivative of each other? Okay, ma'am.
Yeah, that's also true because every linear function is antiderivative because you can find out a function. So this statement is taught in the lecture.
This is there. and antiderivative the antiderivative.
Now there is one thing which is known to be the definite integral. So what is a definite integral? So
The intervals
definite
are
integral is
defined.
nothing but the definite integral is nothing but antiderivative. So antiderivative is actually denoted by integral of. So that's the statement here that the antiderivative. I mean, if you remove the constant, then whatever thing is left, that is known to be the definite integral. So the antiderivative for a function is also known to be the indefinite integral. And it is actually denoted by integration of f of dx. Okay, so this is your capital F, where capital F dash is equal to small. Okay, so here we always assume a constant because that antiderivative. Okay, now let's try to give one formula here. So we know that integration of x to the power n dx is equals to, you guys know, right? X to the power n plus 1 upon n plus 1. So we can actually see this particular definition by this particular example. So suppose this is your small f. Right? Now if you differentiate this function, capital F plus c, so suppose capital F of x is equals to x to the power n plus 1 upon n plus 1 plus c, then your capital F dash of x is actually equal to n plus 1 into x to the power n plus 1 minus 1 upon n plus 1, right? And this is same as x to the power. This is your F. So that's why this antiderivative is also known to be the indefinite integral. And indefinite integral is denoted by this particular sign, integration f of x. We just remove the limits. Is that fine?
Ma'am, please scroll.
This is one example I have taken, how this
Oh, okay.
antiderivative is.
Yes.
Okay, fine. Each other no, this is not correct statement. Madhav, whatever you have written, that every linear functions are antiderivative to each other. This is not true because antiderivative to each other will be only zero function. Right? Just think about it. You will get your answer. Any other doubt so far? The whole
Okay. Every linear functions have a antiderivative.
That's correct. Every linear function have an antiderivative. Because linear function are what? Equation of line, you can say, right?
Yes,
More
ma'am.
or less. Okay. Any other thing? Any other comment you
And
guys want to make?
for the quadratic functions, the antiderivative will be the cubic functions.
Right.
So with the antiderivative, we move higher to the degree of the polynomial.
Because in derivative, what happened? The degree of polynomial reduces, but in antiderivative, the degree of antiderivative, now we can call it to be integration. In integration, the power of polynomial increases. That's why this formula is here, right? The integration of nth power, x to the power n, will become something in n plus 1 power.
This one is the kind of this small chunks, and in antiderivative, we are getting with the whole, the integrative part, hai na?
Right. Now there are so many formulas of integration. I think you guys are familiar with those. You want to repeat those formulas, or is they will be fine? Just formulas are there, their differentiation. Okay. So let's start with the very basic function. So we will talk about a function here. So this is your function. This is the derivative of that function. And this is the antiderivative, or you can say integral of that function. Okay, so let's start at a very simple function, a constant function. Okay, so suppose you have a constant function, then the derivative of constant function, we know that it's equal to 0, and the integral of constant function is nothing but x. Now in place of constant function, if we have a function x to the power n, then what will be the derivative? N into x to the power n minus 1. And integral will become x to the power n plus 1 upon n plus Okay, now these are the polynomials and constant function. Now let's go to trigonometric function. So suppose you have a sine function, then we know that the derivative of sine function will become cos function. So the integral of sine function will become what? It will become minus of cos function, because if you differentiate minus of cos function, you will get sine function. Okay. Similarly, if you have cos function, derivative is minus of sine x, and the integration of cos x sin x. Now, if we have 10x, then we know that the differentiation of 10x will become sec square of x. Right, 6 square of x, and integration will become ln of modulus of c plus. Similarly, 10 in place of 10, if you have now after sign we have cosec x. Right? So the cosec x derivative, if you compute, it will become sec square x. No, it won't be 6 square x. What is the derivative of cosec x? Sec x cot x.
X cot x.
Sec x cot x. Minus of cosec x cot x. And the integration will become ln of modulus of cosec x cot x minus of cosec x minus of cot x. Now say cosec, after we have sec, so sec's derivative is sec x tan x. And its integration is similar type of this, that is ln of sec x plus in place of cot x we have tan x. Okay. Now after 10 we have cot x, so the derivative of cot x is minus of cosec square x, and the integration will become minus of ln of cosec modulus of cosec x.
Sin x.
This is same as sine, because you can take this minus up to here, and 1 by cosec is nothing but sin. Okay, so that's all about trigonometric function. Now let's go to exponential functions. So the derivative of e to the power x is same as e to the power x, and that's why the integration is also e to the power x. Now if we have any constant here, that is e to the power ax, then the derivative will become a e to the power x, and integral will become 1 by a e to the power x. That's the one difference here in between e to the power x. Now, similarly, we can talk about e to the power x. So the derivative of e to the power x is e to the power x log a, right? It's not log, I think it's ln, right? E to the power x ln of a. Ln of a. And the integration will become e to the power x upon ln of a. And now last we have log function or ln of x. So the differentiation of ln of x will become 1 by x. And the integration of ln of x is actually we can compute it by integration by part, that we will discuss it now. And we can see what is the integration of ln of x. Okay, so this is I am leaving it for integration. Okay, so these are the main formulas which we used for computing the derivative of integration. Okay. Now there are 1 or 2 formulas regarding to the inverse trigonometric function also. So I hope let's go and check those formulas. But more or less we just use this. We will use only these formulas. Okay. But we have 3 methods now to compute the integration of any function. Right. So now let's go to the next part, which is the computation of integration.
Plus C we should add, right?
Right. Everything we have plus C. Here all plus C. Also, integral constant. Fine. So one thing is, it is clear from fundamental theorem of calculus that integration a to b f of x dx is equal to f of b minus f of. Right. So this is by fundamental theorem of calculus. Now, as we have some rules for addition, distribution of limit over addition, multiplication, quotient function. Same thing we have for integrals. So that means integration a to b, c times of f of x dx is same as c times integration a to b, f of x dx. And the integration a to b, f of x plus or minus g of x dx. This is same as integration e to b f of x dx plus or minus integration e to b g of x dx. And we can actually change this limit using minus sign. So that means integration a to b f of x dx is same as minus of integration b to a f of x dx. Now in integration, this x is actually a dummy variable. So this is a dummy variable. So in place of x, you can take any other variables also. So that means integration a to b f of x dx. This is same as integration a to b f of t dt. It actually doesn't matter. Whatever variable you will choose. This t, this x, all are only dummy variables. Okay. So they all give us the same integral.
Ma'am, how this magic of sign change we did?
Sorry, what?
How this magical sign change thing we did in this one step? This integration.
This one?
This just build the last which you just discussed, just above it.
This one now. How
Yeah.
it's actually came.
Yeah.
So actually, for this we uses the method of substitution. So this is one method we use for solving the integration. So what does it says? It's actually a combination of chain rule for differentiation and similar kind of thing for integration also. So what does it mean? So suppose you want to compute. So I'll explain this particular thing via this particular method of substitution. So this is one method for computing integration. Method of substitution. So what does you do? So if you have a integration something like this, so suppose a to b, you have one function, but here you have a combination of functions. So that means f of g of x into g dash of x dx. So if you have such kind of thing in your integral, then this integration you can take to be equal to g of a, g of b, and then f dash of t dt. Right. So here what does we do? So we actually take this g of x to be equal to to be equal to t. So take g of x to be equal to t. Then what happened? Then g dash of x is equal to dt upon dx. Correct? Is that step is clear? If you differentiate g with respect to x, then it will become g dash of x, and that is actually equal to dt upon dx. But this is same as g dash of x into dx is same as dt. So that means this whole term, this g dash of x dx, we can replace it by dt. And but now here we have to change the limits also. So if the value of x is equals to a, then what will be the value of t? So the value of t will become g of a. If the value of x is equals to b, then the value of t will become g of b. So ultimately, if you do all the substitution, our integration e to be f of g of x, g dash of x dx, this will become integration g of a to g of b, f of t dt. Okay, now how this substitution yields to that particular result. So if you consider this integration e to b f of x dx, and consider t to be equal to minus x or x to be equal to minus t, right? Then what happened? So then since x is equals to minus t, this dx is equals to minus of dt, correct? And the limits will change. So if I think I missed here, because if x is equals to a, then t will become minus a. Done some mistake here. This property is right, a to b. If we have, then we can actually change it from b to a using f of x dx. Let me see. Okay, so I think we have to use twice this particular one. Let's try it. So if x is equals to a, t will become minus a. And if x is equals to b, t will become minus b. So that means this particular integration e to b f of x dx, now it will change to minus of integration minus a to minus b, f of minus t dt. But we want to change it from b to b. I think we have to take another substitution here. So in place of t, if we take t minus a plus b type of thing here. So because what I want, if x is equals to a, I want t to be equal to b. So if I consider t to be equal to b minus a plus 6, then if x is equals to a, t is equals to b. And if x is equals to b, okay, actually I forgot how to do it, sorry. And let you know.
Can we say that A to B we are integrating and reverse if we are integrating and it will get minus,
Yeah,
so
so
that
that's also correct, that we can say since we are reversing it, it will be minus. But
so
some kind
make
of
it as
proof is there
plus.
using substitution.
Okay.
Okay, we'll see. But this method is actually very useful for computing the integral.
Okay, ma'am.
Oh, sorry. I think I got it. It's very easy. See, integration e to b f of x dx. This is same as capital F of b minus capital F of a. This is same as minus of f of a minus f of b. And this is same as integration b to a f of x. Sorry, I just forget about this. That's how you can prove it. Just by using fundamental theorem of calculus, b to a f of x dx. Is that clear?
Yeah.
Very small thing.
For a moment, I got little heart attack. How this whole mountain is.
Yeah, it's actually not that critical. I thought it was. It's actually not used method of substitution. Just very easy proof using just fundamental theorem of calculus.
Okay.
But although this method is very useful, so suppose I'll give you one integration, try to solve it. So suppose I have integration from 0 to 1 of let's take it to be 2t plus 1. So here we have t square plus t plus 5 dt. Then can you guys compute what will be the value of this integration? I'll give you 2 minutes. Okay, what else we can do? Right? Just what you have to do, you have to take this to be equal to your x, and then this uses the substitution method. So that means, so if you take, so suppose you will take u to be equal to this particular function t square plus t plus 5. Then what is the value of du? So du will become 2t plus 1 times dt. So that means in place of this whole numerator, we can replace this whole thing just by du. Okay, so that means this integration will become integration 0 to 1 only du upon u. But here we have to change the limit too. So the limit won't be 0 to 1. So what will be the limit? So if t is equals to 0, then we get u is equals to 5. And if t is equals to 1, we are getting u is equals to 7. 5 plus 6 plus 7. So the limits will change from 5 to 7 du upon u. And we know that integration of 1 by u will become log of u, right? Because here we have
log u. 1 by
log
x,
u, right?
1 by x integration like
natural log.
So ln of u. So this will 5 to 7. So that means ln of 7 minus ln of. So this is our answer. So ultimately, this method of substitution can be help us to find out a very complex integrations. Okay, is that fine? Any other doubt?
Wait, in that equation, in that integration part, can't we just put in the limits? I mean, subtract the limits by putting 1 and just won't go with this.
No. You cannot directly put 1 because integration is not a limit, right? It's a complex process of finding the area of all rectangles. So that's why first you have to substitute something and then you can. Because we don't have a particular formula for finding integral of such kind of function. We have a formula for x to the power n only, not a combination of x to the.
So how did we manage to edit the limits?
No, actually, it's not that easy because see, integration process is like although very difficult, and since you have a very rational function we have, so we actually don't know how to solve this using integration. Okay, adjusting the limit you are saying, but actually that's not an easy task yet. And although I don't think we can adjust because
No,
function is used for computing the height, right? It's not for.
in the solving of the
Okay.
particular question, we just made the 5 to 7 the limits. Na? It was 0 to 1.
Sorry, what?
In this question that we just solved, the limit we had was 0 and 1, then we got to 5 to 7. This is I've never seen before.
No, this is actually we have to take because this limit are correspond to t, but here we are substituting something in place of t, right? So we have to change the limits too. So if t is equals to 0, then u will become 5 because of this particular expression, 0 plus 0 plus 5, and when t is equals to 1, u will become 7. So you are using substitution, right? So if you use substitution, you have to change the limits too. Okay, so now let's talk about the integration of piecewise function. And then we will go to integration by parts. Yeah, I think that's all we have for this week. Okay, so now integration of piecewise function. Integration by parts and integration of piecewise function. So suppose a function is given to you, which is actually defined in piecewise manner. So that means suppose we have a very nice function modulus of x, right? So it is defined for x when x is greater than or equal to 0, and it is equal to minus x when x is strictly less than. Now, if you want to integrate such kind of function, then how we can do it? Okay, so suppose I want to find out the integration of mod x. So from -1 to 1, modulus of x dx. So then what you will do, you will divide the limit of integration in such a way which will take one of the expressions. So that means here, if I divide the limit from -1 to 0, I will have modulus of x to be equal to minus x. And if I divide from 0 to 1, then I will have modulus of x to be equal to x. So then this integration is actually equal to -1 to 0, minus of x dx, and plus integration 0 to 1 x dx. And these two things are actually equal. So that means integration of a to b f of x dx is same as integration a to c f of x dx plus integration c to b f of x dx, where c is any point in between a and b. C belongs to open interval a and b. And why this is true? Because again, by fundamental theorem of calculus. So if you expand this, the right hand side, you will get f of this is b, f of c minus f of a, and plus capital F of b minus f of c. So here this f of c will get cancelled out. You will get f of b minus. This is the same as the left hand side, f of b minus. So that's why we can actually divide our interval into two or more than two subintervals, subintegrals for calculating the integral of any piecewise function. So here what do we get? We get that integration -1 to 1 modulus of x dx is actually equal to integration -1 to 0 x dx minus x dx plus integration 0 to 1 x dx. Now if we calculate here, it will become minus of x square by 2 plus of x square by 2, 0 to 1, 0 to, sorry, -1 to 0, from 0 to 1. And if you substitute the limit, it will become minus of 0 by 2. Minus will become plus of -1 the whole square by 2. And plus 1 by 2 minus 0. So this is actually equal to 0 plus 1 by 2 plus 1 by 2 minus 0. So that's equal to 1. So that's how you calculate the integration of piecewise function just by dividing your particular integral into required subintervals e to c, then c to d. Is that fine?
Yeah.
Okay.
Once x square by 2 you return, right? From there, how we are dividing minus 0 to 2? You are substituting x as 0 and minus 1, is it?
Just by substituting. Because this is your capital F. So this is f of 0, capital F of 0. So that means minus 0 by 2 plus and capital F of minus 1. So it means minus 1 whole square by 2. Just by substituting 0.
Madam, mod x, how it's came x, madam, here?
See, mod x, that's how we define mod x. So what is the modulus of x? Modulus of x is nothing but x when the x is greater than or equal to 0 and minus x when x is less than 0. This is the graph of modulus of x, right? So this is the line y is equals to minus of x. This is the line y is equals to x. Okay. So if you take any point which is actually greater than 0, the expression will become x. And if you take any negative point, the expression will become minus of x. Then only minus of minus 5 will become 5, right? That's why modulus of minus 5 is.
So in integration, we can take a positive, absolute value, positive we can take, right?
Positive we can take from 0 to 1. And minus of x we have to consider when we have minus 1.
Okay. It's a piecewise.
Okay, fine.
Here is the catch is, if mod x given function for any interval, we can, without this also you can say, without doing integration, simply by understanding this area of triangle of one side and this side.
Right, obviously. Because the length will be 1.
1, half of 1.
Half?
Here half.
Minus 1 to 1 we have. So this length will become 1. So the area will become half. So the area will become half. I mean, just by applying the area of triangle. Right.
Because this is mod is easy. Otherwise it is tough one.
Otherwise it is tough.
Line also you can say. But yeah.
Line also we can say because it will become a triangle only. More or less triangle or rectangle plus triangle. Okay, so that's all for today. I have one topic left, integration by parts, so that I will discuss in tomorrow's lecture. No, sorry. One more thing, that tomorrow we don't have a class. We have class on Monday. Tomorrow's session we'll cancel it. So
Madam,
we will have session on Monday.
Madam, the graded assignment, last week graded assignment, I got doubt. So now you got time to solve.
Yeah, we can discuss. Which question?
Yeah, I'll put in chat, madam. I'll paste in the chat. So
yes.
So, ma'am, that's all for today.
I pasted, madam.
Yeah, that's all for today. I'll upload this particular PDF in the calendar.
Okay. So, ma'am, the Monday session you will take.
Yeah, I'll take Monday session. Tomorrow there won't be any session.
And
so if
you will take one more revision session, na? At the before
that I'm not sure, but I'll take Monday session.
Ma'am, tomorrow we have 8 to 10 and shifted to at what time on?
8 to 10 on Monday only.
So there is a session on Wednesday or what? Tuesday there is a session, right? Solve with us.
Monday there is a session, Tuesday there is a session, and wait a second. So this Sunday session will shift it to Monday.
Thursday also
Tuesday is also session and Thursday is also session. So we have 3 sessions.
Yes, exactly.
Madam, I pasted in the chat box, that question.
Yeah. So this question. So what's the doubt here?
Here,
oh, ma'am, this one I am asking.
So I don't know how to work out, madam. So this is very complex.
Yeah, so here what you have to do, we have to consider the continuity and differentiability of Px and Qx, right? So here you observe that if you take any point between 0 to 8, then it's nothing but a rational function of this type, that is 4e to the power t minus 8 minus 4 upon t minus 8. right? And this function will be continuous for all t not equal to 8, because only 8 will become will make this particular denominator 0. So that's why we know that for all t except 8, this expression will give us a continuous function. And at t is equals to 8, we have a constant function, so we'll take this information afterwards. But here also, if we take any t which is strictly greater than 8, this function is nothing but the combination of log function and the quadratic function. So it will be again continuous for all values of for all x not equals to 8. Okay, so that means the continuity will only bother when we take x is equals to 8. So that's the thing we have to consider here. So if you take x is equals to 8, then since this function is defined in a piecewise manner at x is equals to 8, we have to consider left-hand limit, right-hand limit, and the value of function, correct? So the value of function is 4 here. So what will be the left-hand limit at x at t is equals to 8? It will become limit t tending to 8 of 4 e to the power t minus 8 upon minus 4, and upon we have t minus.
Ma'am,
Now here you
T10
observe.
to 8 minus, na?
8 minus is same as you can take it to be 8, because here the expression is given to us. So that's why same as 8 minus is same as t going to 8. Why? Okay, so see why we can say this, that instead of t going to 8 minus, I can replace t going to 8, because here if you consider this particular function 4 e to the power t minus 8 upon this particular function. So for this function, if you compute the left hand limit at for the writing. So if you consider the left hand limit at t is equals to 8, this is same as the right hand limit at t is equals to 8. For this function, if you consider this to be some another function g of t, then it's very easy to observe, because it's nothing but a combination of exponential function and linear function. But since it's a rational, that's why we cannot say what can happen as we go near to 8. But the left hand limit and right hand limit will be same. So that's the another reason you can actually say that. I mean, see, whenever you have piecewise function, that's how you have to calculate. Instead of t going to 8 minus, the substitute t going to 8. These two limits will be same. Okay. That means this is same as t going to 8. But as you apply t going to 8, it will become 0 by 0. Correct? Here we will get 0. Here we will get e to the power 0. So 4 minus 4 will become 0. Again, we have 0 by 0 form. So we can apply an hospital. So if you apply an hospital rule, it will become 4 times e to the power t minus 8. Plus derivative will be as it is, because it's e to the power x. And minus 4 will become 0. Here will become 1. Now we can actually substitute t is equals to 8. So if you substitute t is equals to 8, you will get 4. So that means the left hand limit at 8 at t is equals to 8 is same as 4, which is same as the value of function. But since we have to also compute the right hand limit. So for right hand limit also we will do the same thing. The right hand limit, I think we need some adjustment. Let's see.
Madam, 1 second. So you undo, madam. So how you got 4 actually? So.
See, just apply L hospital.
Okay, so then you are substituting 8, then e power 0, it's a 4. Okay.
E to the power 0 is 1. So
Okay.
this 4 will remain as is. Okay.
Okay. Then minus 8 also we need to substitute, right?
Minus 8 means?
Which means t tends to a plus u substituted. Then same way t tends to a minus a.
No. See, this 8 to the power minus and this minus 8, they are not same. So this 8 minus means we are approaching 8 from the left hand side.
Okay, understood. Sorry.
Okay. Fine. Now we have to compute the right hand limit also. So right hand limit, I think. So right hand limit also we have which form? So if you substitute 8 here.
The second one directly we need to consider, madam. So t equal to 8 means 4. That's it. We don't want to prove anything, right? This.
Right. Why we don't want to do that? Because here we have this exponential function, and exponential function are continuous, right? So the limit will be equal to value of function. So that's why.
Okay.
Fine.
Okay.
Yeah, I know all these. I mean, sometimes it's very difficult to say when we have to put the value and when we don't have to put the value. But whenever you think that, okay, the function is continuous, then we can actually substitute the value. Because that's the definition of continuity, that limit is nothing but equal to the function. Just think about it. So now what is will be the right hand limit at t is equals to 8. This is again equal to limit t going to 8. Sorry, 8. 4 times t square minus 64 to the power 1 upon ln of t minus 8. Now here I think we have to do some substitution here because this will
T square
become
minus 8 square.
Yeah, t square minus 8 square, that's correct. So 4 times t minus 8 into t plus 8 to the whole power 1 upon ln of t minus 8. Then what? Because
Can we
here
substitute
we
T here?
have, if you substitute here 8, it will become 0. 0 to the power 1 by
Infinity 0. 0 to the power
ln
0.
0 to the power minus infinity will become, no? No, 0 to the power 0 only. Minus infinity.
So again,
So whenever we have, yeah, we have to do some log trick here, no? Whenever we have 0 to the power 0 type of thing. There is one trick which we use for simplifying such type of functions. So suppose whenever we have 0 to the power 0 type of situation, so for converting this into 0 by 0 or infinity by infinity, we uses some log. Right? So we apply some log here and then compute it. So here if you consider L to be equal to 4 times t square minus 64 to the power 1 by ln of t minus 8. Okay, and apply ln both sides. So ln of 4 is same as ln of this whole quantity. Then what happened? We have this property that ln of x to the power a is same as a ln of x. So because of this property, this whole term will be in the front. So that means it will become ln of 4 t square minus 64 upon ln of t minus 8. Now here it will become minus infinity by infinity, minus infinity by minus infinity case. So now we can apply a L'Hospital rule and then take this ln back. So that's the thing we have to do here. I think it will take time. But what are the answers here? I think PT will be continuous then.
We don't know, madam. So that's one thing. Here only the number of correct statement, which one is correct, totally you're not able to predict. So if you're checking with co-pilot, also not different answers are coming. So we're not clear actually.
Okay. So let's try to solve this sometime. So one thing is see, this is the pure algebraic stuff, what I'm telling you, that observe the limit and all those things. But one
Become a
I
pile
should not
of
tell this. Sorry, what?
Your screen not.
Yeah. So let's solve this question. See, so far we know that left hand limit of this p of t at t is equals to 8 is equals to 4, which is equals to p of 4. Right? Now we bother about the right hand limit. So what will be the right hand limit? So right hand limit of p of t at t is equals to 8 is actually equal to limit t goes to 8 of this particular expression. Whatever expression is this expression. So that is 4 times t square minus 64 to the power 1 by ln of t minus 8. Okay.
Yeah, we'll take log.
Now, so here observe that this is some 0 to the power 0 type of, right? But we can apply an L'Hospital rule only for 0 by 0 or infinity by infinity. So whenever such kind of situation happen, we'll take this to be some number. So let's take it to be equal to L and then compute ln of it. So ln of L will become ln of this whole quantity. That means 4 of t square minus 64 to the whole power 1 by ln of t minus 8. Okay. Now this is same as, now because of the log property, this term will jump out and it will become ln of 4 of 64 upon ln of t minus 8. Right.
Yeah.
So now here
Yeah,
we know that since ln is continuous function, so yeah, right. T goes to 8. This is 8 ln of L is actually equal to limit t goes to 8. This whole thing, right? 4 times t square minus 64 and upon ln of t minus 8. Now here we can apply L'Hospital rule. So by L'Hospital rule now, it will become upon 4 of t square minus 64 into 2t. It will become 1 upon t minus. Just the differentiation, right?
मैम
Yes, yes.
80 होगा मैम 8t not 2t.
Why it is 80?
4t
See,
square मैम
the 1 by 4, right. Sorry. Thank you. 80. So limit t goes to 0. So it will become 2t and this will go into the numerator and this will come into denominator. So it will become t minus 8
And
and
we can
upon
expand
t
t
minus
squared
8.
minus, yeah.
This will get cancelled out. So now it will become limit t goes to 0. This is 2t upon t plus 8. Now this is continuous function again because of rational function.
So ma'am, we have to divide by t.
Divide by t.
No need here. Okay,
No,
continue.
limit is 0, madam. So what is the limit actually? That piece actually?
2 by 8, 1 by 4. Correct?
No.
0.25 is that.
Sorry, what?
Madam, t is greater than 8, right? So
sorry.
the limit.
Limit 10 to 8, right?
Limit 8 होगा मैम.
हाँ तो limit बन गया 16 by 60. That means 1. Correct?
So which is discontinued.
No. We have computed the limit of ln, right? So that means limit t goes to 8 of ln of L is actually equal to 1. So that means, yeah, it will be discontinuous. L will be e to the power 1. So it is not equals to. So they have given discontinuous or continuous. What are the correct statement?
It is discontinuous, yes.
Right. So p of x will be discontinuous. So obviously it does not differentiable.
Differentiable.
Okay. So
And
whenever
this
px is
model
continuous, we
is
can.
Madam, now it's now discontinue understood. Now, but we are differentiated, right? How it not differentiable?
Because we know that if a that every differentiable function is continuous. So that means if a function is not continuous, it cannot be differentiable. That's the fact we can use. So we know that every differentiable function is continuous.
Okay. If it is not
So if a
continuous,
function is not continuous, then obviously it cannot be differentiable. So you
but
can say that
above, but above we differentiated, right? So we differentiated ln. Okay.
No.
You're telling the comparing with the continuous function. Okay.
We not entirely differentiated. We differentiated one part of function, right?
Okay.
The differentiability also breaks only at t is equals to 8. The function will be differentiated all other terms.
Okay.
So one thing I want to say, but you can actually use Desmos to solve this question very easily for continuity also, for continuity at least.
Okay, how will you plot this this 4e power? Yeah.
Yes.
The PT, how we are
we checked, madam, up to that is stopped one area. It's not going. That graph is not going actually. Somewhere it is stopped actually. I checked actually.
Okay.
So means it's not continuous. It's correct only.
The question didn't end yet. Actually, QT also is there. No?
QT also there.
Okay. So yeah.
That is easily observed that modulus function will be negative. It will be like a sharp corner.
Correct,
No, it
correct,
will be
correct. So
continuous and it is sharp corner, not differentiable.
not differentiable. So not differentiable at
But it is
t is
continuous.
equals to 0 to, yeah, it will be continuous.
Yes,
Modulus
yes.
function is that. So it will be
Always
continuous.
continuous.
So that means
So first
P
option,
QX is continuous.
first option is not continuous. For that, it is
Not
not
continuous.
differentiable. So we are
Right.
closing. And second one is continuous. Then and differentiable,
Both
right?
function PT and QT are not differentiable. So this is correct. PT is continuous. This option is not correct. QT is continuous. PT is not differentiable. This option is correct. Neither PT nor QT is continuous. This option is also correct. No, sorry, not correct because QT is continuous. So the correct answers should be 2 statements.
Yes.
Yeah, two only, madam.
Hmm.
Not differentiable. Okay, madam. Another last question, madam. If you have time, maybe you can tell. So
Yeah,
last,
just paste the.
yeah, I'm
Or
just
else we
pasting
can
now.
discuss it in Monday session because Monday session is open session. So there we can solve the question.
Okay.
Because what we'll do on Monday then? Monday is open session, so there we can solve all the
Yes.
doubts.
We can make.
So, ma'am,
Mhm.
before Monday, there is any other session?
No. I don't think no. There is no session.
Okay.
So Monday is your last session, right?
Monday is yeah, maybe. It depends on circumstances. If someone is available, then they will take the result.
Excuse me, ma'am.
So
you are not continuing here?
Ma'am, is there any revision sessions?
Madam, Monday calendar is not reflecting. So year after only we'll plan, huh?
Yeah. I'll shift it this Sunday session to Monday. Because
Okay.
Sunday I have another session. So
Okay.
we'll take Monday.
Excuse me, ma'am.
Yes.
Ma'am, can you refer some book for linear algebra and calculus?
For calculus, we have that Thomas Calculus, Pearson's publication. For linear algebra, actually, there are so many books. So it depends on which purpose you want to say. So if you want to refer for basic linear algebra, then there is one book called Friedman something, Linear Algebra by Friedman. So this is a very basic book for linear. So you can refer that. Friedman's Linear Algebra. There is one another book that will be little standard, the Hoffman comes. Sorry, what? Someone want to say something?
Why is Monday the last session?
No, Monday is not the last session. We have
was
two
telling
revision sessions too. No. He asked that Monday is your last session of what?
No, ma'am.
so
You try to
planning
take
to
a
leave?
more number of sessions, not on Monday.
Yeah, I'll try. Yes, Shidhar, what?
Are you planning to leave?
No. Where I'll go if I leave this?
No, because it says your last session, so I was wondering, is there any? Because I was
No.
in and out.
No, the next week is her last session, I was asking. Because next Vishal will be taking the class of revisions. Yeah, that's what I was asking.
No.
Before
The thing
quiz
is,
2.
I was actually I missed most of the conversation up on this thing. So suddenly when I hear that, I thought maybe some major changes have happened. So that's the reason I just
Before quiz 2.
Okay.
Yeah,
Ma'am,
before
I
quiz
have
2.
one doubt. One
Yes,
small.
Niranjan.
So I got actually on the first quiz I did not appear because I was not qualified. I did not completed my assignment. So now I have eligible to do the qualifier on this 1st December. But the syllabus will be first 4 weeks or the from week 4 to week 8 for me.
For re-qualifier, you are asking, na?
Yeah.
So for
He is not qualified yet.
I'm not qualified.
so he will so you will go for re-qualifier exam, na? So for re-qualifier exam, the syllabus will be 1 to 4 only.
It will be 1 to 4 only because I got a mail that says that quiz 2 will be there from week 4 to week 8.
Yeah, quiz 2 will be there from week 4 to week 8. But if you are going for re-qualifier exam, since you are saying that you are not qualified, so you'll go for re-qualifier only, na? You won't go for
Right.
quiz 2.
Okay,
Madam,
so I have to focus only on week 1 to week 4, right?
Week
Okay.
4, right.
So for us, quiz 2, we can only focus on 5 to 8 only. So it's okay, right? So we don't want to.
I think there are 1 or 2 questions from 1 to. I'll ask to Vishal sir about this. That we have questions from 1 to 4 on.
Okay, okay,
Or
okay.
else they will tell you in the revision sessions also in
But
details.
okay, but earlier previous time and all. So 1 to 8 or 5 to 8, madam?
In the previous terms, we have 1 to 8 only. There will be very less number of questions from 1 to 4. 1 or 2 questions from 1 to 4. But the maximum weightage will be from 4 to 8.
Okay, madam. Okay.
And ma'am, can you suggest something to study the first 4 weeks?
First 4 week, I'll just say that just go through the content, practice assignment, activity question, graded assignment. That's it. Just do this much. Put your 100% on this material only. See, because if you
There are
completed
so
it now,
long
so you will
videos,
get more than 80%.
because there are so many videos, like in week 1
Niranjan.
only there are 15, 20. Shall I just refer your theory summary sessions, which is 1.5 to 2 hours on YouTube?
You can check that also, but yeah, you can check them also.
Okay.
Niranjan, could I ask if you don't mind?
Is there any revision sessions?
Yes, Sridhar.
From week 1 to week 2?
Hello.
No, somebody was talking, so I was waiting.
Oh.
I think Lokesh was asking something to Samiksha.
Yes, Lokesh. Hello.
Lokesh?
Yeah, ma'am. Is there any revision sessions, ma'am?
Is there any what? Revision session, if you are asking, so yeah, there will be 2 revision session.
Okay. Niranjan, I just want to ask you, like, because if you are going to rewrite the qualifier, I mean, it's good that you're continuing with the course, but it's going to be 1 to 4. I mean, you can put a lot of effort for the qualifier, am I right?
Right.
You have to go redo the whole thing.
No, first time
Of
I
course,
was
it's a
not
wonderful course,
qualified
but
because I did not completed the assignments on time. So that was the pre-requirement to.
yeah. No.
fully
What I
finish.
want to ask you is, like,
Uh-huh.
in your case, it's the redo qualifier is only from 1 to 4. Then why are you? I mean, I think in the last session also you told you are continuing this thing.
Yeah,
I do
actually, I
understand you like
just
it,
came here
but
to check, like if I can get any, guidance on how to prepare 1 to 4 weeks. Oh, that's why I was just waiting to finish the session so I can ask, ma'am.
no, I think somebody told, one of the instructor told you. Sorry, Samiksha, we are holding you for something. I think one of the instructor told you that actually the qualifier percentage this time was comparatively low or something. I don't know which session was it. I forgot also. It's hardly some
It was
20% or 30%.
statistics. Yeah, that was for statistic. But that time I did not ask like what will be the syllabus, like whether it is going to be first 4 weeks. So I thought just I'll ask in
Okay.
this
I think
session.
we should cut short because somebody wants to ask something to her.
Okay.
Thanks. Okay.
Thank you. Bye-bye.
What's that? Yes. Well,
Yes, ma'am, I have a query that I have submitted my documents for after qualifier for course registration, but my documents are still not verified, and my dashboard has not been updated up to week 5 and above. So what should I do? Because there is a quiz 2 in a week.
okay, so can you give me your mail ID? In the
Yes,
chat
ma'am.
box, just pin to me. Star, whatever my name is there.
Yes, ma'am.
Give your mail ID. I'll try to check your dashboard. Have you mailed to support team about this?
No, ma'am, I didn't know what to do. That's why I was asking you.
Okay, yeah. So what you can do, once mail to the support team also, I'll also check your ID if I am able to, or else I'll go to them and ask them to check your and let you know in the Monday session if possible. Yeah,
Ma'am, I have given the ID.
yes. Okay, fine. I'll try to check. Oh, wait. Guys, tomorrow there will be a session because I got the message from Vishal sir. There will be a session on Sunday itself. The session won't get shifted. I just saw the message. He messaged
8 to 10.
me at 8 to 10. Tomorrow is Sunday, 8 to 10, there will be a session. So if you guys have any personal group or something, you can message everyone else to join tomorrow's session. Okay, tomorrow will be a session.
Okay, ma'am.
I
Ma'am,
just got the message.
when we will be introduced to the student community, as it's been 2 to 3 months, I didn't have any interactions with any other one except this meetings.
Okay, so yeah, I also don't know how to put that, but yeah, I'll send one mail. I'll ask him to send one mail too, because since I already announced that there won't be a session at Sunday, but now he says that there will be a session at Sunday. I think Samriddha will
Anyway,
take that session.
people will watch calendar, madam. So otherwise, no worry about that. Yeah, no worry about that. Yeah.
And ma'am, one more thing.
Yes.
I wanted to ask you. आपने गेट क्लियर किया था कि जेई से फिर आपने वहां पे एडमिशन लिया था मद्रास में?
No, जैम की गेट के सिमिलर एक और एग्जाम होता है, जैम, जॉइंट एंट्रेंस एग्जामिनेशन फॉर मास्टर्स. तो उसके थ्रू आई मीन उसमें 5 पेपर होते हैं. इट्स फॉर एमएससी पर्टिकुलरली. सो अगर आप उसको क्लियर करते हो. क्या
आपका मैथमेटिक्स में था?
हाँ, मेरा मैथमेटिक्स में. मैथमेटिक्स, स्टैट्स, फिजिक्स, केमिस्ट्री और बायोटेक होता है, उसमें 5 पेपर.
उन 5 सब्जेक्ट्स में?
नो, मतलब हर एक सब्जेक्ट का एक अलग पेपर होता है. ऐसे 5
अच्छा.
सब्जेक्ट में वो पेपर होता है. हाँ, तो
Similar to
जिसमें
GATE.
भी अगर आपको जाना है आप कर सकते हैं.
Similar to GATE, am I right?
Sorry?
Similar to GATE.
Similar to
something.
GATE, correct. Just replica of GATE, but much more theoretical than GATE. GATE is based on much more application.
Technical stuff.
ओके. और मैम इसके ये बीएससी के बाद भी हम सीधे मास्टर्स के लिए उसमें मद्रास में अप्लाई नहीं कर सकते ना? हमको भी गेट देना पड़ेगा?
हाँ, गेट जैम देना पड़ता है. गेट तो नहीं, जैम देना पड़ता है. बस गेट नहीं दे सकते हैं. मतलब गेट का सिलेबस बहुत ज्यादा मास्टर्स लेवल का है अभी तो मैथ्स के लिए. मास्टर्स करने के बाद ही आप गेट दे सकते हो.
अच्छा, मास्टर्स के बाद गेट देते हैं?
हाँ, मास्टर्स के बाद गेट देते हैं. बीएससी के पहले, बीएससी के बाद में.
Or after the BTech, am I right?
हाँ, after the BTech. Because BSc is 3-year degree, so they won't.
But I mean, if you finish BS, then we become eligible for that.
हाँ, for BS or any equivalent 4-year.
4-year course.
BSc is just 3 years. So.
Only as of now, IIT Roper is through now without gate, I think.
IIT Roper.
Because like this particular program, they have put a tie-up with IIT Roper, and based on the grades and so on, without a gate, I think people can continue.
For BS program.
And even they can do projects, BS programmer.
Mm-hmm.
With high grades, some 80% or something they have put up, and it's a direct, and also some project can be done before that, if I'm right. There was an article somewhere.
Yeah, they have uploaded some of. IIT Roper they have uploaded.
Ma'am, we can give gate after this BS program, right?
Yeah.
You can, I think, do the gate after this.
Okay.
Excuse me, ma'am. मैम गेट के लिए जो मैथ का सिलेबस है वो टर्म 1 और टर्म 2 में अपना मैथ का जो सिलेबस है उतना ही है या फिर और भी कुछ पढ़ना पड़ेगा?
हाँ, उससे भी हायर है. क्योंकि
तो उसके लिए मैथ कहाँ से पढ़ सकते हैं मैम?
उसके लिए मैथ्स बिकॉज उसमें काफी सारे मास्टर्स के कोर्सेज है, जैसे फंक्शनल एनालिसिस हो गया, रियल कॉम्प्लेक्स एनालिसिस, टोपोलॉजी हो गया. ये सब बहुत मतलब मास्टर्स वालों का सिलेबस होता है. तो उसके लिए तुम कहाँ से पढ़ सकते हो? एक तो कुछ एकेडमी है, कुछ प्राइवेट एकेडमी है जो लोग कराते हैं, वो तुम ज्वाइन कर सकते हो, या आजकल अन अकेडमी पे भी होता है कोर्सेस. अदरवाइज यू फॉलो द स्टैंडर्ड बुक, दैट विल बी बेटर. बट
कौन सी बुक मैम रेफर कर सकते हैं?
स्टैंडर्ड हर सब्जेक्ट के लिए अलग अलग बुक है. बहुत सारे सब्जेक्ट है उसमें. फंक्शनल एनालिसिस है.
आपने जो कैलकुलस का बताया था अभी, थॉमसन बुक, वो
हाँ, उसमें कैलकुलस, उसमें सिर्फ कैलकुलस का पार्ट है. बाकी जितने अगर आप गेट का सिलेबस देखोगे तो उसमें नहीं कुछ तो 9 से 10 सब्जेक्ट है प्रॉपर. सो हर एक तो हर एक पैराग्राफ के लिए आपको अलग बुक यूज करना पड़ेगा। तो अगर आप बीएस से हो और मैथ्स के थ्रू जाना चाहते हो तो थोड़ा टफ है। आप जो आपका बीएस का, जैसे आप कंप्यूटर साइंस के थ्रू भी जा सकते हो, तो वो
डेटा
गेट
साइंस से
एग्जाम
जाना
ज्यादा
चाह
इजी पड़ेगा।
डेटा
डेटा साइंस भी
के लिए
होता है
जाना
शायद
चाह
आजकल। हाँ, तो उस हिसाब से आप सब्जेक्ट और सिलेबस देख के जा सकते
And people of data science are eligible for MSc Mathematics in IIT?
हो। या दे आर एलिजिबल।
और मैं तो सोच रहा था कि इसमें अब एनसीईआरटी खरीदूंगा, एनसीईआरटी 11 12 वो बुक से हो जाएगा।
नहीं।
No.
जैम के
So,
सिलेबस में भी तुम्हारा रियल एनालिसिस आता है, तो
so Samiksha, this you are talking about your bachelor's, then for the master's you joined the IIT. IITM.
हाँ, फॉर मास्टर्स आई हैव जॉइंड आईआईटी फॉर
Okay.
एमएस।
But you have 3-year bachelor's or 4-year bachelor's?
3-year bachelor BSc, and then I qualified JAM, and then I go to
Oh, for the
MSc.
JAM you can take a 3-year course is eligible, is it?
हाँ. That's why the
okay.
GATE JAM is similar to GATE, but
But the
using JAM
eligibility
you
is
can
different.
only apply for BSc. Sorry, MSc. You cannot go
बैचलर
for MTech or MS courses.
I understand. Okay.
मैम आपने बैचलर कहाँ से किया था?
So some local college.
Okay, ma'am.
Thank you, madam. Good night.
Okay, thank you guys. It's already.
Thank you so much.
I have uploaded the PDF, so you guys can go.
Where is it?
In
The chat?
In the calendar.
No, the calendar.
एंड देन आप अभी पीएचडी कर रहे हो?
नहीं, job.
टीचिंग
Samiksha,
मतलब इसमें
GA thing has been loaded, all the thing.
Sorry, what?
The graded assignment solutions are loaded because last week we are requesting you for that.
So I told them she will say she will upload all the solutions. So I'll check once.
Check that, yeah. Because all the
Thank you, ma'am.
kind of hardly we have few days time.
Right.
Thank you so much.
I'll
Thanks a
check
lot.
once
Good
also.
night. Good night.
Okay, thank you,
guys.
ma'am. Good night.
Thank you, ma'am.